Should I get started? I'm really happy to see that there's no exponential decay in the number of students, which is very good. The plan for the lectures was this, and we are kind of like still in this standard overview, but let me just give you a very brief recap of some of the really fundamental aspects which I wanted you to take away. I should have just made this one slide. So I think I explained to you that the two photon decay rates play a really big role in the recombination process. Lyman alpha is not the strongest transition. The Lyman continuum is totally blocked, and these two channels to recombine are really competing with each other. They're basically both playing a similar role. Yeah, this is really fundamental because low probability processes like a two photon decay from a metastable state. This is you know, normally you would say, let's forget, right? And then of course I told you that these initial ideas of how to calculate this, they were of course improved on with RecFast, where more levels were included and treated. And I also will continue now explaining what kind of things were still missing. But this was, you know, something which was already fundamentally important for analysis like even WMAP data at the time, right? And then I showed you this long list of processes, which we didn't have any time yet to really treat fully, of course, but just to give, I hope I gave you some flavor of the atomic physics and radiative transfer which goes into this. And in particular, again, I want to highlight two photon decays here from higher levels, from the 3S level and 3D level, which you normally would totally forget about. They play a big role in the recombination process and correct the recombination rate. Just because of these, you know, you can't take the 1+1 photon picture for these transitions. You need to treat it as one quantum act, and you get these profiles which are modified and therefore change the differential probabilities of emitting and absorbing photons. And similarly, the Raman processes. So this is really interesting atomic physics, and the formulation of this in a radiative transfer language is actually not standard textbook stuff. You needed to really sit down and do this. And we, of course, didn't have time to really explore all of that, but this is the movie which summarizes, again, these aspects of the radiative transfer and two photon decays and so on, where you get this time-dependent emission and absorption, and feedback processes and all these things which have to be solved when you really want to reach the percent level precision. Yeah. So this is kind of where we stopped yesterday. Let me switch to the continuation from there on. I think I can stop this. Great. So this is where we were. And I now wanted to just give you RecFast was adding higher levels, as I told you, but it only added the levels as one equation per shell. So you change the principal quantum number n, and you have one additional equation. But of course, you understand that there's sublevels, the angular momentum substates, even the magnetic substates in principle, but those you can forget about. But the angular momentum substates are not something you can forget about. Yeah? So the standard assumption is that, and that's what RecFast basically did, that the sublevels in one shell are basically given by the statistical equilibrium expressions, where you have just a statistical weight of 2l+1 divided by n squared for the level. So you can assign one total population of the second shell, third shell, fifth shell, 100th shell, 300 shell, right? And just populate the sublevels in this way. But this is not possible and correct, because imagine you have an atom with all these sublevels and all these transitions among the sublevels. The transitions, of course, because of dipole selection rules, are restricted. So an electron sitting in this level cannot easily go here by one transition, because the delta L plus minus 1 basically forces it to cascade down along this, you know, sequence, which means it's much, much slower than, for example, going from an NP level to the ground state, right? Because that level, in principle, you can have a direct transition to the ground state. And normally, at least when you do stellar astrophysics or stellar evolution, then the statistical equilibrium assumption among the sublevels is justified because of collisions. But I told you, collisions are really not important in the recombination problem. They allow, for example, they enforce us to take into account these two photon decays. If we had collisions, they would also be destroyed. So then it would be a 1+1 photon decay. Yeah? So collisions are not relevant, and that means you have to treat these sublevels more carefully. And then in addition, one of the really crucial things is recombination is not equally populating the sublevels. It's much more unlikely to reach the hydrogen atom into the high L states than into the low L states from the continuum. Which means that unless you have a process that lets electrons move into this direction and then populate everything, this is not working. Yeah? And that, of course, means now that your problem, instead of scaling with just the number of shells that you're including, you're scaling now with the number of shells square, basically. Yeah? So, and here's the detailed calculation that we did, which was a full following all levels. And if you go here to 300 shells, we did up to 500 shells explicitly. When you're talking about 500 shells, you're talking about 125,000 equations which you have to solve. So in parallel, you have to follow the evolution of these populations to do this, right? Of course, that's an approach which, and I will tell you at the end, that you can actually overcome this hurdle. If you want to do a case by case, you can actually integrate out these higher levels. But when you want to know the physics and what is the recombination process, then you can do this explicitly. And if you plot here again, the changes in the ionization history with respect to the old calculation as a function of this number of shells, then you can see at high redshifts it doesn't matter so much. Why? Because at high redshifts, the recombination rate, so the rate at which electrons enter the atom, is not really the bottleneck. It's the Lyman alpha transition rate, the Lyman alpha blocking. But at late times, Lyman alpha becomes more transparent, and you can speed up the recombination process, and then you're bottlenecked by the slowest process, and that's recombination. So capturing the electrons and getting them into the atom is the hard part at low redshifts. And then you see that you're actually depending on the number of shells. So if you increase the number of shells, your recombination rate increases, and you're basically recombining faster. Yeah? And you can see that that this process it converges when you go to something like 300, 400 levels, shells, excuse me. You will be able to start converging, right? It's increasing, and your recombination freezes out at some point. And the correction at late times is something like 1.5%. 1.5% at late times, the maximum visibility function is around here. So this is not as important, luckily. But if you want to get the dynamics right, this is what you have to do. Yeah? And you can think about it very simply. When you increase the number of shells, you're effectively making the total atom bigger. And that means you have more cross-section to capture electrons. Right? And the reason why this was possible to do is because the matrix, which is describing these transitions, is very sparse. And this is here just an illustration for a 20-shell hydrogen atom, and here's the helium atom. You can see these patterns, and when you reorder them a little bit, you can see that it's a very sparse matrix because of the delta L plus minus 1 selection rules. We also included quadrupole transitions, which is delta L plus minus 2 and 0, and that doesn't make any big difference, of course, in the whole calculation. And appreciate as well the complication of the helium transition and matrix is way bigger, because I told you that there's fine structure and all these things. Okay, and so I told you again, the recombination rate increases, and you're recombining faster and faster, and then this converges, if you will, at some point at some 300, 400 shells. And you wouldn't expect too many changes when you go to 1,000 shells, for example. But 1,000 shells is, of course, quadratically more expensive. The other thing that quenches the levels is collisions. But it turns out that when you include collisions, the most important collisional rate that you have to include is the rate that diffuses electrons across a shell. Because delta L, just skipping in the same energy level doesn't cost energy, which means it's much easier than, for example, transitioning between some shells or transitioning to the continuum, right? So if you include delta L plus minus 1 transitions, and then again as a function of the maximum quantum numbers you include, you see that you again this changes the recombination rate. And it changes the recombination rate, and but the effect is limited to something like 0.1%. And there were new works a couple of years ago now, which included even delta L plus minus 2, plus minus 3 transitions, just to describe the collisional rates. right? And we actually checked that, and it doesn't make a big difference. Even if you're able to jump 2 levels away, right? It means that you're diffusing faster, but it doesn't make a big difference. So for the recombination dynamics, this is a less than 0.1% effect, so one can in principle neglect it. However, of course, it is included at least to leading order. And I told you that there's quadrupole transitions, which we included for hydrogen as well. This is basically nothing else than different transition rates we included among the high levels as well. And but all these corrections are very small. Here is a factor of 10 to the 5. So these are tiny corrections one can forget. But it's still, we obviously try to check. All right. So that's kind of my overview of the hydrogen recombination physics that I wanted to give. And again, I want to emphasize it's all standard atomic physics and radiative transfer, but done carefully. Yeah. So there's no. It's just. Let's get rid of the assumptions that are incorrect at the level of precision that we need. Helium, of course, has in principle exactly the same list to go through. Helium has neutral helium has a slightly more complicated spectrum, as I told you as well. So there is a few more complications in connection with quadrupole transitions. In fact, they have to be treated, in particular from the low energy levels. But the helium recombination process happens at higher redshifts and is basically in a bath of electrons which are not yet recombined with hydrogen. That means you're not bottlenecking yourself as severely as with hydrogen, because you always can find a hydrogen, an electron that belongs to a hydrogen atom, let's say, to help you recombine. And because helium abundance is 8% relative to hydrogen, that means that you have a lot of electrons to take care to play with. So all these dynamical processes are not as important, so you don't need to treat as high a number of levels, in principle, to do the recombination calculation properly. So something like 20 or 30 shells is enough. You do need to take into account spin-forbidden transitions, so transitions between triplet and singlet states, which initially was not taken into account. But if you look, and this is one of the things I really want to emphasize, the original rec-fast calculation is this curve here. So again, free electron fraction at this high redshift now. And you see that helium recombination is basically merging with hydrogen recombination, right? It's just happening simultaneously almost. And then, of course, when hydrogen starts recombining, helium is really also very, very low probability, right? So this is not correct, because even when you just include the spin-forbidden transitions between the triplet 2p states to the ground state of the singlet, already then you accelerate the recombination process and get quite significant change. You can visually see it. This is not the same for hydrogen ever, because in hydrogen it's always like a few percent or sub-percent. Here you can see it. It's of course again relative to hydrogen just a 1% effect, but it is a big effect in terms of the helium recombination process. And then a very beautiful, I just want to point out this transition was already known in 1977, so it could and should have been included in principle. But one of the things that is really beautiful, just like with hydrogen, Lyman alpha, you have the helium resonances, main resonances. The photons are stuck in these resonances, right? They scatter and they have to escape. It's very slow. And this is even true for the quadrupole transitions, and the spin-forbidden transitions are less optically thick. They are only optical depth of something like order unity or a few. So they are not trapped as strongly as, for example, the Lyman alpha, which has optical depth, the Sobolev optical depth of 10 to the 8, right? But the interesting thing is, those photons, which are emitted in a helium equivalent of the helium Lyman alpha line, those photons, they are not very far away in terms of absolute distance. So these are at like 20 eV or 21. And we, of course, know that the continuum threshold for hydrogen is 13.6 eV. So this is not extremely far away. The cross-section goes like 1/nu to the third power. So this is still having a very significant probability to absorb a photon in the helium line. And this process, even though at that time at that redshift of 2000, there's only a tiny amount of hydrogen atoms in Saha equilibrium, in fact. So a very small fraction, 10 to minus 6. This small fraction of these hydrogen atoms, because of the strong, the big cross-section, they can even then still absorb photons in the helium resonance. So if you now absorb a photon in the helium resonance, it creates a continuum electron. That electron loses its energy quickly, and then it is basically recombining to the hydrogen atom because the hydrogen atom became unhappy by that process because it wants to be in Saha equilibrium, and that means you have actually removed an electron or a photon from the resonance, and that means an electron of helium can go to the ground state. So you're basically giving it a backdoor exit. And that accelerates recombination, and it looks like this. And you can really distinguish now in the modern calculations between helium and hydrogen recombination. So here's a radiative transfer calculation of, again, the escape problem of the resonances. So here's these main helium lines. Here's triplet. Here's a triplet or a triple of quadruple and singlet and triplet singlet transition lines. And you have to solve all of these when you want to, again, get high precision. And this is, in fact, only done in CosmoRec in the latest version of CosmoRec, treating this very carefully, how the feedback between these lines go. You can even include things like electron scattering, but not only in the diffusive approximation, which in fact turns out to be incorrect. You need to do it with the kernel approximation, scattering kernel. I don't have time to go into details, but you do all these feedback processes. So let's look at this movie one more time. So just like hydrogen, the lines become active, they build up. We are still at very high redshifts, well before the recombination era. Then you have this, the lines from the third shell. They start really, feeding back into the hydrogen, into the lower levels, and you have all this dynamics. And then at some point, you see how now the helium recombination process goes on, but you now see that the overall level of these photons goes down. This is precisely due to the fact that hydrogen becomes more and more populated and can actually absorb those photons. And now they become much, much sharper. The features, they can't even feed back anymore between the lines because before they reach the lower level, they're absorbed by hydrogen. And then at some point, the helium photons are even completely gone. They are just absorbed. So the high energy helium photons above the Lyman continuum threshold of hydrogen, they're basically being destroyed. So this is a really interesting interplay between helium and hydrogen, which is crucial for the dynamics of helium recombination. All right, so why is all this important? And Rashid yesterday forced me already to say a little bit how big the effects are, but I'm now going to show you the cumulative effect on this of these corrections. So this is just a reminder. I told you the visibility function is crucially determined by the free electron fraction. That means if you change the free electron fraction at some level of 1%, the visibility function will also change at a similar level, right? Order of magnitude. And in particular, changes around redshift 1100, where the maximum of visibility function are most crucial. So if you compute now the relative changes of the most detailed calculation with CosmoRec compared to RecFast, then this is the shape, this is what you will get. So you see that relative to RecFast, helium recombination is accelerated. The effect is something like 3 point something percent. Now, again, this is well before the recombination era of hydrogen, where the visibility is the most important, and this is the part which is really the crucial part. So this is not making as big an effect, yeah, in the dynamic, in the CLs, but it is noticeable because it's a very big one. Yeah? Then all this changes here around recombination. There's a delay basically here and an acceleration in the earlier phases. Yeah, and this is this is coming from all these things like the transport in the Raman processes and two-photon decays and Lyman alpha transfer, scattering, electron scattering. All these things are in there. And then at late times, the freeze out I know I just want to clarify. So this is because it's with respect to rec fast, which was done with a completely different calculation. When you here compare, you see that it is looking like a delay, right, in the capture rate. So the sub levels is a delay. I said it incorrectly earlier. So with respect to assuming that there is angular momentum substates are in equilibrium, you are overestimating how fast you can do because the substates are not populated in the same way. So when you say you treat the sublevels separately, you actually slow down recombination. Yeah. So anyway, so here the effect is 1.5%, but again, this is in the freeze-out tail of the recombination history, and it's in the late part of the visibility function, so it's not as crucial. If you just plug in Cosmorec into the calculation of the CMB power spectra and then compare to the old rec-fast calculation, you get this kind of level of changes to the power spectrum. So there is basically additional damping, and you can see here is the temperature power spectrum and the EE power spectrum. Yeah. So the effect, in particular at large, at high L, small scales, is quite significant. We're talking about 4%. And as you can imagine, when you have a damping like this, well, this is degenerate with tilt of the primordial power spectrum, right? If you take your power spectrum and just make the NS a little bit steeper, then you tilt it down, and that looks like, in principle, looks similar to the extra damping. And then, of course, there's a little bit of changes in the phases as well, or the positions of the peaks. But all these things, they are mainly playing with NS and omega baryon. So here's an old calculation that Richard Shaw and myself did. Shortly after Cosmorec was released, we just basically estimated, because the data was not available at that point, this was 2011, we just setting up basically Planck calculations, we estimated what would be the errors that we would get. So the green curves are what rec-fast would have been obtaining without all those recombination corrections that people had worked on for so many years. And you can see that NS would have been biased by something like 3.3 sigma. Omega baryon would have been 2 sigma biased, both of them low. Yeah? And there's even some changes in the amplitude and so on, but you understand that there's always an interplay between combinations of parameters. But the most significant effect in the 6 standard parameter model would have been NS. Yeah? And we also showed in this paper that you can indeed, by just refudging rec-fast, you can capture this. You don't have to really do the full calculation. That's very sad, and I shouldn't be even saying this, because of course I want you to use my codes, but it is not necessary in that sense. So doing a very, very brute force calculation once for the cosmology that we know is in principle enough. But we are lucky, we can do these calculations in 1 second now. Now, some people argue that's still too long. That's why rec-fast is still being used, and it just takes fractions of seconds. And I hope that I can convince you that rec-fast++ is even easier to use and that it's much nicer as well in terms of its flexibilities. So again, this is really a crucial point. We would be talking about different inflation models, right? And we'll show this in a second. So the real biases that we saw or would have seen in Planck 2015, again, in 2015, rec-fast was already recalibrated on the detailed calculations that we carried out, right? But if you ignore those calculations and just do the computation, you see that it would have been nearly 3 sigma. You see that the error bar, the absolute shift is a little bit smaller than what we estimated with the simple, setup for what effective sensitivities Planck has. But in any case, this would have been a 3 sigma shift if this wouldn't have been done properly. And this is, of course, the figure that is very relevant in this connection, because we all know that this plane constrains inflation models, and some of them are ruled out, and some of them here are on the edge. Without the recombination calculations, this whole this whole constraint would have shifted over to the slightly redder side. And that means you would have been, you would be talking about slightly different models. Yeah. So this is quite crucial, and both Cosmorec and HiRec are able to capture all these things. And here's even a figure showing how well all the codes now agree. Again, rec-fast recalibrated on Cosmorec, But the recalibration was actually done in a slightly earlier stage of the full calculation, so there's still a small bias between regfast and cosmoreg, but it's 0.1 sigma, 0.15 sigma for NS. There is hardly any bias between high-reg and cosmoreg, which shows that they are treating the problem consistently in terms of the physics. Now, they don't do both the same physics, because indeed high-reg has several other approximations which cosmoreg doesn't make. In particular for helium, I think there is something to be said, because cosmoreg can actually treat the helium fully properly. Helium is, of course, one of the targets as well of the future. Here's the constraint from Planck again on helium abundance and effective. And these things, these constraints, they would also be affected by these recombination calculations. So if you just, again, using Planck sensitivities, sorry, this is actually cosmic variance limited sensitivities, and then just do a 8-parameter model where you have neutrino number and also helium abundance inside, now you would see that helium would be biased pretty strongly. And S is not biased as much anymore. It's again the interplay between the different parameters. When you open up the parameter space and the way to shuffle around the changes in the CLs, then this would have been is one of the biggest changes. All right, so that was in fact the end of the first lecture. And I think I hope I convinced you that the standard calculations at least are really under control now. And there's no real problem for Planck, and it has been many people who have really helped with this. But I dare say none of them is in Planck. Okay, so for the young people, make sure that when you do something, make sure that somebody told you to do so. Okay, right. The biases would have been significant with, in particular, with respect to the inflation models. That's really crucial aspect of it, and inflation models. And I will now talk about the recombination spectrum, which yesterday would have been tomorrow, but it's going to be now. Is there any questions to this whole first lecture? No? Why don't you have a question? Okay. Well, let's go on. All right, so let's see how far we get with this, but I think we might be able to manage. So the recombination radiation is something which actually motivated us to do this calculations. So Rashid was always just interested in the spectral distortions initially. But because of the spectral distortions, you had to do careful calculation of the levels and so on. So that forced us to do all these things. And then we realized, oh, there's effects. So that was actually the thing that was, quote unquote, more important or more relevant in terms of what people were really interested in, right? So this was kind of like a byproduct, but I think it was at that point, at this stage, the more important byproduct, right? Anyway, the physics is just beautiful. I was just so happy when I did all these things, and that was anyway driving everything. But the recombination radiation, as you can appreciate, every time you recombine to a level, you emit a photon. And this photon will be, going through the medium. And I told you about the Lyman alpha line, how that's really, the photons are trapped in the resonance, but they still at some point escape. So we understand immediately that there should be a Lyman alpha distortion, or a high Lyman series distortion. And there should be a 2-photon decay distortion, because the 2-photon decay is happening as one of the controlling channels. And this is, of course, something that was already realized early on, and just thinking even in the back of the envelope, just asking 13.6 eV of energy was released per hydrogen atom. How much does that mean? That means that you estimate immediately that there should be a small distortion of at the level of 10 to the minus 9, 10 to the minus 8, right? Just because there's so few baryons. The most important aspect here is that because this happens so late, and Rashid will tell us much more about thermalization physics, and Rishi already mentioned as well a little bit, because it's happening so late in the universe, these photons, at least when they escape the lines, they are actually free to go. They don't get reabsorbed, at least in any significant level, unless they're at extremely low frequencies where free is again always relevant. So the Lyman alpha and two photons, this was of course realized already in the early calculations, but Victor Dubrovich was the one who emphasized that there should be recombinations, of course, to the highly excited states. And because those photons, electrons, they trickle down the levels, they will emit many photons as well at low frequencies. Yeah? So it's not only those high frequency resonances, but it's also low frequency. And when you do the calculation, this is what we did in 2006, 2007, and 2008. We did the calculation for a 100-shell hydrogen atom. So at that time, we were still having a hard time doing 100 shells, which is just 5,000 equations. But you can see here the beautiful fingerprint of the recombination process. So the two lines are, one is without helium and the other one is with helium, or with the effect of helium included and without helium included. And you can see here at high frequencies, again, this is the distortion from the CMB microwave background black body, which we would see today, which of course means it's redshifted. So Lyman alpha would be appearing at something like 1.7 terahertz, or somewhere within the terahertz regime. And then you can see here Balmer alpha, Paschen alpha, bracket, and you see all those lines, all those alpha transitions, they peak out. And the shape of these lines is reflecting the dynamics of recombination. The shape changes. If you change the recombination process, you will change these shapes. So that is a direct way to learn about the recombination dynamics. And of course, these distortions, they depend on the parameters, which means you can in principle do independently cosmology with this. You can actually, in principle, measure parameters, and I will mention that a bit more. So here's a picture just to highlight these lines. They are appearing at very different phases than, for example, the CMB anisotropies become visible. Last scattering surface and visibility function is redshift 1100, something like 270, 280,000 years after the Big Bang, right? Then the hydrogen lines, they come actually from redshift 1400, which is slightly earlier, 100,000 years earlier, right? And the neutral helium and doubly ionized, singly ionized helium lines, they come from even other earlier epochs, which means by looking at these lines, you have a tracer or a messenger from these eras, right? And it's really interesting that if you, of course, if something non-standard happens between these eras, like energy release or something unexpected, then this will affect directly the spectral distortions from the hydrogen and helium plasma. So this is a really interesting way of looking beyond the last scattering surfaces, if you will. And the reason why I'm, of course, very excited as well is because we now can do these calculations, including 500 shells for hydrogen, helium, both helium ions, in basically 15 seconds on my laptop. So this was taking 6 days on a supercomputer when it was 100 shells back in the days. And the improvements I will try to explain in connection with the recombination dynamics. The improvements are that you can really integrate out these higher levels and basically treat them in an effective way. And there's lots of physics included in these calculations. So here's the solid black line is the total of hydrogen and helium, and here's the individual helium cases. So the neutral helium has even some absorption features because of singlet-triplet transitions and things like that. And they are small absorption features because you can basically reshuffle electrons in some way to reach them faster, to make them reach faster to the ground state. They're not just forced to go downwards; they can actually go upwards and take a loop to another level. That means you get an absorption feature. Yeah. It's quite interesting. It's the total helium dynamics. So a lot of physics is included. So for example, electron scattering for the singly ionized helium recombination spectrum is actually relevant because at that early time, the scattering broadening due to line scattering, due to electron scattering is non-negligible. It's at the level of 10%. And you can see the difference in the helium recombination spectrum for the singly ionized helium, hydrogenic helium case. the lines are broadened and smeared, it would be, otherwise they would be much more sharp features. Yeah? Then you have to take into account all these feedback processes between helium and the neutral helium and singly ionized helium. So here's a shape of the spectrum. Without these feedback processes is the red line. And with these feedback processes, you see that there's actually quite strong enhancement of the emission in the low frequency parts. Yeah, it just comes from the fact that when you have a high energy photon from a singly ionized helium line feeding back onto helium, it makes an electron go and take another route, another round. And that means it has a probability to emit at the low frequencies, and that enhances all these spectral features. And similarly, to take all the feedbacks between hydrogen and helium photons into account, and you can see that this does make quite significant differences. I want to emphasize, these differences are not tiny, right? Helium is only 8%. So you would naively say, well, at most I have a 16% change in the recombination radiation. Indeed, on average, that's probably true. But locally, you can see that there is enhancements by quite some amount, just because these features or these photons are not emitted just uniformly. They are emitted in lines, and therefore they enhance locally. They can become quite visible, right? So, I told you always the role of collisions is negligible for the recombination dynamics. It turns out for the recombination spectrum, you do have to include them at the low frequency part, right? Because, of course, where the low energy transitions, they are much more easily perturbed by collisional processes, and that's what you really see. And the most relevant change is coming from the L-changing collisions, so within a shell, so that you're just transporting electrons across a shell. So I just wanted to highlight this. But measuring at these low frequencies will be extremely hard, and the spectrum also becomes extremely smooth. So this is more of a statement of showing where the effects are important and how one can visualize them. So as I said, we can now do these calculations in 10-15 seconds on my laptop, which means you can really do parameter estimation in principle. Right? You just, like in the good old days of CMB, you can just say, well, what happens if I change my parameters, like the helium abundance? You see that when you change the helium abundance, the spectral distortion from the recombination process changes quite visibly in terms of its spectral features, right? And when you change the baryon abundance, you see that this is more of an overall up and down, rather than a change in the spectral shapes. There's minimal small changes, of course, because the dynamics of the recombination process is affected. Escape probabilities and all these things, they do affect things, but the main leading term is just an overall rescaling, because if you have more baryons, then you have more hydrogen atoms. I mean, the fraction of hydrogen atoms increases, and the amount of hydrogen increases when you increase the baryon number. Right. There's one thing that I actually wanted to mention. Of course, in the recombination calculation, when you change helium, the biggest effect is that then you have more or less hydrogen, because changing helium, so increasing helium means you're reducing hydrogen. That means the real effect by changing helium is coming dominantly from the fact that you're reducing hydrogen, and that means the redshift 1000 part of the visibility function is actually directly affected as well. Just one thing to highlight. Of course, here you're directly seeing helium in principle, right? Because you have its contribution and it changes directly. All right, so of course the question is, can we observe this? And one of the experiments that was on the market for many years now, in fact, is PIXI, and I think Rashid will probably also mention. PIXI is a spectrometer which is also having polarization sensitivity, a Fourier transform spectrometer, and it was going after B modes, which you heard about as one of the most important drivers of all the activities nowadays. And a really, really important target for the future, just to understand inflation and potentially prove its origin and the energy scale of inflation. But then also improving limits on mu and y to measure, energy release processes. The sensitivity of PIXI I forget if I have actually put a figure, but the sensitivity of Pixie is unfortunately not enough to reach those lines, because they would basically be, maybe on average you would be able to see them, because there's of course a contribution on average to all spectral bands, but you would need a factor of probably an order of magnitude better sensitivity. There is, however, some ideas which you might have heard of here in India at the Raman Research Institute. Apsara is the idea to measure the recombination features at the very low frequency part of the spectrum. So yeah, if we go here, you can see that there is, in this regime here, 1 to 10 gigahertz, there's several ripples. Right? And ripples are very hard to mimic by instrumental things or by foregrounds. And in this part of the spectrum, the foregrounds should be more or less smooth. It's like synchrotron and radio emission from galaxies. So there's a hope that by just integrating for a long time, you might be able to reach to this nanokelvin level signals. Now, in terms of relative sensitivity, at this frequencies, the spectral distortion from recombination is actually at the level of 10 to minus 6, 10 to minus 7. Relative to the CMB. But of course, there's many things which are way above the CMB at those frequencies as well. But there is some ideas, as I said, to measure specifically in the 2 to 6 gigahertz regime, and potentially, see those ripples. It's very challenging, obviously, and it won't be done immediately and tomorrow. But it's not impossible. At least estimates that we did with Mayuri Rao and Ravi Subramanian and at the Raman Research Institute. So the question is, of course, what would you learn? And I already mentioned it several times. You can, in principle, do things like, measure the baryon density, right? The overall amplitude of the spectral distortion. You can, in principle, measure T0 in an independent way, because the position of these lines will depend on when the recombination happened. And when you change T0, you can actually shift basically the moment of recombination in terms of its redshift. The helium abundance, I showed you this movie, how the features change their shape. That is a direct reflection of the helium abundance. Obviously, again, we're talking about then, when you take into account the constraints we have, we're talking about small effects. But of course, there could be non-standard things happening during helium recombination, which we're not actually sensitive to directly with, for example, the CMB anisotropies. Yeah. So either way, helium abundance is some target, and then the recombination process, we're happy about the calculations now in the standard physics, but these could be modified by processes we haven't accounted for. And that means that you can, in principle, by looking at the recombination radiation, you could test the recombination paradigm. You can really ask the question, is the recombination process really happening the way we think it is, right? And one way to see this is the helium spectrum. This is just a calculation that José Alberto Rubino Martin and myself did a couple of years ago already, well, many years. And it was dealing with the, I told you about the absorption of helium photons by hydrogen, neutral hydrogen, and how it accelerates the recombination of helium, neutral helium. And when you accelerate, that means you make features sharper. And that is exactly what you get. You will, the faster this recombination process around helium recombination is, the more sharp the features become, and you can even see 3 absorption features in the neutral helium spectrum. Whereas when you do this is the case which is most close to the real case, you see that it's only 2 features. And here, if you make much slower recombination without this absorption included, you see that there's only 1 feature and very broad spectral distortion. So the shape of the lines directly depends on this. I think that's pretty clear and understandable. And if you have things, and I will talk about these non-standard recombination scenarios a little bit more in a second as well. If you inject energy by decaying or annihilating particles, or you add extra ionizations, you're basically saying, well, the electron that is already happily sitting in the ground state goes to the continuum again and does another cycle, right? And then you might, depending on how much this annihilation or decay rate is, you might do that several times. And depending on when it happens, it will add features to the spectrum or additional emission to the recombination radiation in a time-dependent manner. And this is one calculation that I did in 2009, just showing that when you assume annihilation of dark matter happening, that you can in principle modify these spectral distortions. Now the annihilation rate, which is assumed here, is very high compared to the allowed constraints from CMB anisotropies, but this is just to demonstrate that you actually are sensitive to these kind of aspects. And decaying particles, for example, during helium recombination, well, I can tell you they are not constrained directly by the CMB anisotropies. So you can in principle change the helium recombination process quite significantly if you want, without being ruled out. All right, so this means that recombination radiation is a way to test, basically before the last scattering surface, test physics of the early universe. And non-standard thermal histories, you can reconstruct the recombination history. It's actually something that my student Luke Hart is looking into. Just changing the dynamics of the 2s and 2p level, you will change the features, and then that way you can even test the dynamics of those transitions, right, or those levels. And you can distinguish between pre- and post-recombinational Y distortions, because if there's a Y distortion, and Rashid, so the Sunyaev-Selvidge effect at high redshifts, the Y distortion, if that is present, it changes the recombination process as well. But I don't have time to go. And there's even, of course, possibility of fundamental constants varying, which change the energy levels or the transition rates, and in principle that leaves features. So these are all possibilities for exploration, of course. But I think one of the key things is the recombination radiation is a fundamental signal from our universe, early universe. It should be there, and we believe it is happening just the way we all hope it is. So we have a clear target, and we could in principle just say, let's design an experiment and try and go after these signals. And because they have so many features, even though they are at very low level, because the baryon number is so small, so low, we should be able to see these in the presence of foregrounds which are smooth enough, for sure. Yeah. It's not going to be easy, not tomorrow, but it is a target, and it is a fundamental property of our universe. It's a signal that should be there, and we can shed light on an era that we haven't tested directly in that way. Like, for example, the helium recombination eras. You haven't directly tested those, right? All right, so let me talk a bit about non-standard recombination problems. The first thing that I want to highlight is, although I told you how important the 2-photon decay rate is, the 2s to 1s, in the lab, this decay rate is in fact not measured well. So theory, second order, perturbation theory, quantum mechanics, we can calculate this very precisely, and we know it's 8.206 transitions per second. Now there is, at the last digit, there's already some changes when you do different gauges and so on, so there is corrections already at that level of precision. But we can calculate this from our quantum mechanical description. But measurement is something like 40% error, simply because preparing a hydrogen atom and letting it rest in the lab for 8 seconds without perturbation is very hard, right? You can imagine that this is not an easy thing. You need to excite it with some lasers, and then you need to look. The biggest probability is half of the excitation energy, and so it's complicated. So there's many perturbations. It's not measured well. Planck is directly sensitive to this number. So Planck can, in principle, determine this number. It's atomic physics with cosmology, if you will. And just by changing the two-photon decay rate, the standard case is the solid black line. If you decrease the 2-photon decay rate, well, you understand, recombination is slower, so you're going in this way. And if you're increasing it, it means you're accelerating recombination, just like with the stimulated 2-photon decay. That means you're going back and forth here. Yeah? And the CLs are, of course, responding to it, no surprise. And if you then run the data, Planck data, and ask what the value Planck is preferring is, which is a calculation we did in 2015 with Planck. Excuse me, I really should use a different font, color. 2015, then you see that you get from Planck a value that is consistent with the 2-photon decay rate that we all expect from theory. Now, there's two reasons why this is not necessarily, it wouldn't be necessarily the case. One is, well, maybe the calculation is wrong, which is the most unlikely, yeah. But it comes out the right way, right? The second is there could be some systematic in Planck or another process that has that correlates with this kind of changes to the visibility, yeah. So the fact that although if you add this parameter, you basically get still the consistent result and a proof that this number is good, and it was now redone in 2018 as well, and the number has even gone closer to the expected value, just because there is indeed some improvements of the data and constraining power from polarization. This is still a really interesting and nice test. And it was an improvement by at least 4 times over the existing experimental value. So it's kind of neat. Yes? No, simultaneously. It's a seven parameter model, yeah. 6 parameters plus this, so 7 in total, yes. Exactly, yeah. So I mean, again, I'm not trying to tell you, I mean, there is ways to change the two-photon decay rate. So if you have varying fundamental constants, you can in principle affect this, and I will talk about that as well in a second. But it is a beautiful test of the consistency of the Planck data, internal consistency, and well, you get a value. You have a measurement. It's nice. And you can, in a similar way, by allowing the CMB temperature to vary around recombination, you're sensitive to that, because the CMB temperature changes, again, the position of the visibility function. And it's not the only effect, because, of course, angular diameter distance, or theta, last scattering, the angular scale, sound horizon, and so on, they are also changing, so there's correlations there. But even when you change the CMB temperature, you can get a parameter constraint on the CMB temperature directly from Planck itself, which is independent of the local measurement that Firas did. Realize that when you do this at redshift 1000, it's a different era in principle, so there could be changes, and we even were initially thinking maybe there's some way to reconcile these Hubble tensions by doing something like that, but it doesn't seem to be working. And the constraint on the CMB temperature is something like 3% is the error bar, which is way weaker than what the error bar is from Firas, but it's a different era. Okay, annihilating and decaying particles. Maybe first I should say, well, of course, we are all pretty much still in the dark about what dark matter is, right? And the WIMP scenario, which was one of the most popular, or is one of the very popular ones, is becoming more and more, restricted by experimental constraints, direct measurements, indirect measurements, and that's why we are, of course, now looking for other possibilities and going into the directions of axions and, primordial black holes, these kind of things. But you can constrain annihilation and decaying dark matter scenarios, great, with the CMB anisotropies. And it's, again, you're not going to be surprised when you dump some extra energy, you're basically ionizing the medium a little bit more, right? And that changes the recombination history. And here is some early calculations, old calculations from 2004, 2005. There's even earlier calculations before this, but this is some of the calculations that really have sparked interest in this direction by Chen and Kaminkowski, and this is a figure from Padmanabhan and Finkbeiner. You see that the freeze-out tail in particular changes. So dark matter annihilation is an n-square process, right? You have a collision of 2 particles, and you annihilate, and depending on the mass of the particle, that's the amount of energy you get. And of course, there's all kind of complications related to what kind of decay channels you have, where's the energy really going, how is this energy being transferred, and I believe I have some slides on it. But the point is, the visibility function changes. Here's the visibility function. It changes as a function of this decay rate. That means the CMB anisotropies, the power spectra, should change. That means you can constrain this. Right? So here's a figure illustrating a little bit. This is from Tracy Slatcher's work. There have been many people working on really specifically calculating those efficiencies of dumping energy into the transitions, into the excitation. into the ionization and heating of the medium. And Tracy Slatya is one of them who has done a lot of work on this. Now, these efficiencies, they are, no surprise, strong functions of the time of the redshift where you're at, because of course at high redshifts the medium is much more dense and processes are much more fast. You change the importance and relevance of different aspects of this problem. But it turns out, when you look at efficiencies as a function of decay channels and so on, so this is here electron and positron channels and then muon channels, most of them are around the recombination era where the constraint is driven. The constraint is driven by this era around redshift 1000. In fact, when you really look carefully at it, it is more like coming from redshift 600, 700. And I'm out of time, but I will ignore. We will. In any case, the point is that you have these efficiencies of how the energy, which is coming out of the decay or annihilation, how this energy reaches to the recombination process, and that does reflect in the changes in the CMB anisotropies. And I already mentioned that there is, of course, effects on the recombination spectrum. So here is a figure summarizing the constraints that Planck was obtaining in 2015. These constraints have not increased dramatically now with the 2018 constraints. There's some improvements, but I still have this old figure. Here's, as a function of mass, this sigma v cross-section interaction, annihilation cross-section. You normally constrain S-wave annihilation, where you know that this is basically constant with time. And there is this efficiency factor, which is precisely what I already mentioned, because you know that the different channels of decays, they heat the medium in a slightly different way than they ionize the medium or excite the hydrogen atoms. There is an effective fudge factor which you can put, and this adds a level of uncertainty because this factor can range from, all the way from 0 to unity in principle. So, for example, if you have neutrino channels, then you know that all the energy which you're dumping into the medium goes into neutrinos, and you should look at the neutrino background rather than the recombination lines or at the CMB anisotropies, because they are not affected by it, right? But of course, if you have leptonic channels, electromagnetically interacting channels like electron-positron pairs and so on, then you will have some effective decay deposition rate, and this is typical in the order of magnitude 10%. So here's what you would like as a thermal relic. If you're just thinking about the WIMP scenario, this is the band which you would be expecting, and this is the part which is ruled out by the data. And the constraint is stronger here because when you have a lower energy, you get more particles. And because of the n-square dependence, there's actually one factor you gain in total as a function of mass. There's all kind of interesting things like Sommerfeld enhancement when you get this collision of the annihilating particles at low velocities. They can in principle be colliding more quickly because of this Sommerfeld enhancement process, and that of course would change basically these overall constraints up and down. So here's some of the models that were favored by AMS and Pamela, the electron-positron excess. But these seem to be in tension with the data from Planck. Now, again, one should be very careful because, of course, the Planck data is, quote-unquote, a different era. And if there's indeed Sommerfeld enhancement effects and so on, there's complications in the total interpretation. And then here are some models that are, favored by things like the Fermi bubbles and galactic emission. Either way, these constraints, if you just improve the sensitivity of CMB experiments to the cosmic variance limit, then you in principle would be able to reach into this direction and rule out more of the parameter space. But the improvement is not extremely huge. It's not orders of magnitudes anymore. We're talking about factors of maybe 1 order of magnitude. Yeah. And decaying particle is a slightly different aspect, of course, because annihilation happens more or less equal. I mean, it's a broad energy release history. It happens at all epochs at some level, and depending on what's the annihilation cross-section, of course. Whereas decay is something which happens in a specific, in particular for particles which really have a lifetime shorter than the age of the universe, the current age of the universe. It happens at the localized, most effectively in some localized redshift band, right? And so you can in principle think of using this to reionize or pre-ionize the medium. You can in principle say, let me have a decay happening so that it changes the ionization history around or before reionization, right? And Viviane Poulin has done some nice work on this, modifying class and including decaying particles as the possibility. Now, of course, we're normally hoping that we don't have a particle that really completely decays, because we are normally thinking of dark matter as the origin of it, and we don't want to get rid of all dark matter. But if you say there's a fraction of dark matter which decays, then you can still play with this in terms of like localized energy release. And then you see that you can in principle, here's the standard recombination and or ionization history, that you can in principle pre-reionize the medium. Yeah, and just one other example for this idea, dark matter, we don't know what kind of structure it has. There could be excited states in dark matter, which are, excitation like a hydrogen atom, and they could be long-lived or metastable, and in principle could could depopulate at those eras, right? So there's games one can play, but the most important aspect is you can, in principle, look for constraints. And here is a constraint on the lifetime of these particles or these levels and the efficiency at which they decay and release energy. Yeah. So these constraints are pretty tight, and they are complemented by constraints from CMB spectral distortions and BBN for the short-lived particles. But at late times, it all comes from the fact that you change basically the ionization history in the post-recombination era, and in that case, you become sensitive directly to the presence of these extra decays. And of course, one can also talk about primordial black holes potentially even evaporating and things like that. So there is models in which you can play with these games. So it's just to say that this is not just crazily out of reach. And it is one thing that you can do with the CMB data. Okay, I'm wondering what I should do. I have a little bit about primordial magnetic fields as well, and non-standard recombination histories in model-independent way, and then I think I'm done. But maybe I will just ask you guys for questions and not keep you from lunch, or if you give me maybe 5 minutes. Okay, it will be 10 minutes, I am afraid. Yes? Okay. Rishi is the boss, and he allows. Great. So primordial magnetic fields, they can dissipate their energy. Just like decaying particles and annihilation, you ultimately are ionizing or heating the medium. And primordial magnetic fields in particular, they are really heating medium, because you have these magnetic fields and they set up motions with the electrons through the Lorentz force. And then because of viscosity in the medium, in particular turbulence and so on, they start releasing their energy, and that heats the medium. And if you have a faster electron trying to recombine with a hydrogen atom, then it's harder, right? Because if you have a very slowly moving electron, it gets deflected much easier than if it's fast, right? So you recombine slowly, more slowly. That means when you do these calculations, here's the standard recombination scenario, and when you now add these extra heating processes, you can see again that this freeze out is changed. Now, there is, of course, this aspect now that if you want to distinguish this from decaying particles or annihilating particles in particular, maybe you remember this looks very similar. So there is, of course, problems in that direction. If you really want to do model comparison, CMB anisotropies are not as powerful. But it's really interesting to see, and I will get back to this figure later, or tomorrow in fact, you can see that these constraints are pretty tight when you just include this in the calculation of the CMB anisotropies and then do the parameter constraints with 2015 data. And we now updated this as well with the latest data. You see that these constraints are pretty tight, tight in comparison to what the CMB anisotropies directly give. So this is confusing because CMB anisotropies are, of course, dynamically affected by the presence of magnetic fields as well. So they change the way the modes propagate in the early universe. And that is an effect where you can also be constraining through CMB the magnetic fields. And the level of constraint is normally something like a few nanogauss. So 4 nanogauss, for example. These constraints are in fact tighter. So when you add the ionization history changes, you will get a tighter constraint. And this was initially discussed by Schiff, and then Kerstin Kunze and Komatsu followed up on this, and we did also some work. And one of the most important things is that these calculations are unfortunately very rough. They're, like this. And we did now a real MHD simulation, obviously with approximations. This is still not the final answer, but we just said, let's add a power spectrum of primordial magnetic fields, Gaussian initial conditions, and let's ask how the power spectrum evolves as a function of time. And so here's the power spectrum. We're talking about very small scales, in fact. So this is unfortunately not in the right units. This is actually 10 to the 3, 10 to the 4 inverse megaparsecs. We're talking about very small primordial magnetic fields at very small scales. Initially, it is just a power law. We put in this case, the quasi-scale invariant magnetic field. And this is giving you the energy per mode. And then initially you see that there's just exponential damping, just like with the CMB power spectrum. You just damp away those modes by photon viscosity, in fact. But then at later times in the post-recombination era, or in the recombination era, you see turbulence develop. You see that this spectrum, which is here, now it reshapes into a power law which is consistent with Kolmogorov turbulence. Now, I'm not claiming that we have solved turbulence because that's a really, really hard problem, but it is really the velocities that start driving up because electrons, when they disappear, that means that you have less coupling to the photons, and then the few electrons which are still there, they can go much faster. And in that way, you can build up velocity fields, and that means you have more nonlinear effects and you get turbulence. And if you calculate the energy release rates at different redshifts in this process, then you can see that in contrast to previous calculations, I'm not going to go through this, it's a little too messy, but in contrast to the previous calculations, the real heating through turbulence is actually something that sets in quite gradually around recombination. So here's the real heating, and it peaks beyond the recombination, the redshift 1000 universe. Most of the heating is actually delayed with respect to the recombination process. And it is sensitive to the initial spectral index, to the initial magnetic field strength, and so on. The calculations are quite time-consuming, and we will soon update, using these new calculations, update the way these constraints from CMB anisotropies were derived, and hopefully get some more robust answers. And then we will also be able to really claim that CMB anisotropies are most affected, for example, by ionization history rather than the dynamical effects which are changing the mode propagation. But this is an open question. It could be, my feeling is that it's actually going to make the constraints slightly tighter from when you do this properly. But we are playing with this. And variation of fundamental constants is one of the things that people have been looking at as well, where you just change alpha, or the electron-proton mass ratio, and because all these quantities that are relevant, for example, the 2-photon decay rate depends with the 8 power on the alpha, on the fine structure constant, that means that you change the recombination dynamics, and of course, one of the most important aspects is that the transition frequency changes with alpha as well, which means you're shifting the energy thresholds back and forth. And that means when you're looking at the ionization history, you move basically the time of recombination back and forth. And this is some game that many people have played before, and my student Luke Hart was looking at this in particular as well. And then the CMB anisotropies are changed, no surprise. But you can also do time-dependent changes of alpha. So why would alpha change? Of course, this is non-standard physics, but if you have the presence of scalar fields or extensions to standard electromagnetism, you get, in principle, potentially some of these changes. Changes can be appearing. And so if you just assume there's a power law change around recombination, you can see that you now get a differential change in the recombination dynamics, because it's no longer just one overall kind of back and forth, but it's actually changing differentially. And the nice thing is, this is Luke, he's normally much more happy, but he was probably working overnight. Anyway, the differential changes are actually not degenerate with the changes back and forth, because one of them changes the visibility function maximum back and forth, the other changes more the width of the visibility. So you can actually independently constrain them, and here's a summary of some of those constraints that we did in 2015. So here's the best constraint on alpha, and you see that it's consistent. It's just scaled by the standard value. It's consistent with the standard value at a very high level of precision. If you do this with changing alpha in a time-dependent way, you get also a very tight constraint, and you get a constraint even on combined. And one of the interesting aspects is that when you now do Planck 2015 with BAO and all the constraints we have, you can actually start breaking some of the degeneracies between changes of the electron mass, but you should think about this as changes of the electron-proton ratio. And here, the Feinstein structure constant, the constraints from 2013 are very weak and degenerate. It really fills, it's basically two independent constraints. And then when you add BAO, you can actually start breaking some of those degeneracies. So this is something which is nice, and RecFast++ has that implemented, so you can actually just change alpha and just see how the recombination dynamics changes. And I think I will not go through this, but there is also model-independent ways of doing constraints, where you just say, let me do small perturbations at different times in the recombination dynamics, and then ask what kind of shapes, what kind of eigenmodes of perturbations are actually the most constrainable. And this is a movie, which I think is where I'm going to stop. It shows when you do these perturbations, what is the response in the CLs? So now you're approaching the visibility function, and now you see the response is quite large. Then it goes down, and then helium recombination, you're already not seeing any real response anymore. And if you have these responses, you can then diagonalize the response, basically information matrix, Fisher matrix, and in that way you can get modes that are constrainable. And Planck has done these things, and we have shown that there's no indication for a real departure from the standard recombination scenario. This is work with Mazia Fahang and also Dick Bond, which we have been pushing in the last two parameter constraints. And here, this is really the slide I'm stopping. If you do the same for perturbations in alpha, you can see that the responses in the ionization history, they are a little bit different. They are no longer peaks but they have like this tape. And the corresponding responses in the CLs are shown here. And then here you can see, even at helium recombination, you can still get some small response in the XEs, but here the CL response is very small. So we are now redoing the analysis and basically doing a diagonalization again and trying to then ask what kind of time-dependent changes are most constrained by the data and allowed by the data. And the nice thing is that then you can project any of your non-standard models onto these modes, and in principle say, without rerunning the data even, you can say which models are constrained and which ones are unconstrained. So that's where I'm going to stop, and then tomorrow we will just talk about the recombination codes and an overview, and I will walk you through some of the codes. Great. Sorry for keeping you longer. Thank you. Oh, and if there's questions, of course. Everybody's hungry. Great. Well then, thank you. I think we go.